this. Okay, so as I said, here's where we left off. I'm going to go back a little bit just to review. We talked through, basically, we had put through right here what the ALU actually looks like if we had correctly constructed all the possible data paths. Everything from the control unit, which we had left out multiple times, we have put in here now, to the registers, to the actual ALU, shifting, the PC just incrementing by 4, and then finally writing back to memory. And there's some other write back paths that we'll talk about that go down here and go back around to write data. Does anyone have any questions on this big picture from a review perspective? Okay, I'm going to move forward then. So that up until now has all been presented as basically a single data path, okay, and a single data path of like the life of 1 bit, okay. Obviously, our processors don't do a single data path and a single bit contiguously, right? When we're running operations on our computer, right? There's much more going on with that. So we use pipelining, right? So pipelining basically, and the book gives, I'm going to use the book's example because it's reasonable, a laundry example, right? And it's kind of, it has some humor, right? It says, what do you do when you wash your clothes, right? And it gives like a college example, right? So it says, first you put them in the washer, then you put them in the dryer, then you fold them, and then you ask your roommate to put them away, right? And so that was the humor of the book put in that order. But kind of plotting this out, if assuming each of these actions takes 30 minutes, right? If you wait for every action to finish, right, how long is it going to take you to do 1 load of clothes? 2 hours, right? So if you only do that and you wait till every load of clothes is finished before you start washing another load, right, and you have 4 loads of clothes to do, how long is that going to take you? 8 hours, right? Now, obviously, maybe you do. Please don't be insulted if someone does their clothes that way. That's your choice. I don't do my laundry that way. Usually, I try to put as much as I can in the washer in the first load, and then if it doesn't all fit in the first load, then I wait till that load finishes, and then put it in the dryer, and immediately put another load in the washer, and hopefully that's it. And then I start pipelining. So basically, that's what the bottom shows here, right? That as this set of clothes finishes washing, it gets put in the dryer. Well, that frees up the washer for a new load of clothes. So if you did this with 4 loads of clothes, then instead of doing it in 8 hours, it would take 3.5 hours. So it's parallelism, and it's a significant speed up. And of course, we have to turn it into a formula, even if it's washing our clothes, because this is an engineering course, right? So here's the formula, but it also applies to pipelines with CPUs, right? That you take, this number is presuming that the stage takes 0.5 or half an hour, okay? So this isn't a standardized formula. You'd have to put in whatever the starting cycle cost is. Maybe it's 200 picoseconds or something. You'd have to put that number in here. In this example, what's put in here is literally what the starting cycle is, which is a half an hour. And then you add to that what it costs to finish the remainder of a single process. So in this case, the wash, dry, fold, and launder. So we already took care of the 0.5 for the start. Now the 1.5 is the remainder. And then n times the number of stages you have available, right? And then right there, that would tell you how long it would take. But we want to calculate the speed up factor, right? So the speed up factor up here is already calculated for us, right? Is when we said we did them just one at a time contiguously, it takes 8 hours. But when we stage them, right, in a pipeline, it takes 3.5 hours. So the factor is 2.3. So using this formula right here, you can calculate the factor. Here's the bottom line, is generally your improvement, speed up, is going to be equal to the number of stages. So more stages, the faster overall your computing is accomplished. Now, as you can see here, n goes to infinity. So theoretically, you could make a chip with an infinite number of stages, and then everything would never take longer than whatever your startup cycle is and the cost of the cycle, right? That would be it, right? You would only, nothing would ever take longer than this, basically. Everything would follow that. But obviously we're constrained. We can't have infinite number of stages on a CPU, right? For power and heat, amongst space, other issues. So that's pipelining in a very simple, now applying that to real life for this course, right? In a MIPS pipeline, here's what we've talked about, and I tried to talk about in the first lesson of the course, right? Is generally we're gonna deal with our instructions in this manner, right? We're gonna fetch them from memory, we're gonna decode and read the register, we're gonna execute it, which is the ALU portion, then we're gonna determine what we need to do with memory, and then write it back, either to the register or to memory. Well, this is very nice that's been presented in fetch, decode, execute, and write, right? I've kind of presented in that manner throughout the semester because this is very easy to break up into stages, right? So we can just break each of these into a stage. What does that look like on the CPU? Well, if it's a clocked CPU, which all of them are that we work with generally, and it's not asynchronous, so it's a synchronous CPU and it depends on clock cycles, it's going to look something like this, right? In the instruction fetch on the rising edge, I bet you can't read that in the back. It's going to go get the instruction and it will be available by the time the falling edge occurs, okay? So we're talking about, I mean, fractions of a second, right? Just for it to go through that combinational logic and into the sequential logic. All right, in the next stage or clock cycle, it's gonna figure out what does that instruction mean, right? It just pulled memory. It has no clue what that means, so it's going to decode it. And by the falling edge, the register information it needs will be available. Following that, right, it's going to actually start processing it through the ALU, which is the execute portion, and the result of the combinational logic, there may be some sequential logic in there or stored memory, will be available on the falling edge. And then finally, what are we going to do in the memory, and then writing it back, okay? Now this is highly simplistic, okay? There's a lot more than this, but this is just a starter example. Does anyone have any questions so far? Okay. It makes a little note here, sometimes we can do a write back to a register. We're going to talk about that more, but it's not saying we can go back in time or anything. It's hard to see in a linear process. It'll be easier to see in a pipeline. So let's talk about putting this all in a pipeline. For example, I don't like the order of these slides. One second, let me find what I want. Hold on. I'm going to use the book. The book has a nice picture of putting it all together, what it looks like. For the pipeline of our MIPS instructions. Let me find it real quick. This is somewhat reasonable. So right here, that's big enough to read. You can see, so it takes that Datapath logic circuit for the MIPS ALU that I just showed at the beginning of this class and breaks it up into the different portions, right? Into the fetch, the decode, the execute, the memory access, and then a write back, okay? So those essentially are your stages, going from left to right, okay? Does anyone have any questions on that? Now there's one thing unrealistic about this. This is just to kind of get you thinking on how do these stages work. What has to be in between? Man, this is hard just to stay here to record this video. I like walking around. What has to be in between these two stages if there's a clock cycle that's happening in between these? And this isn't just combinational logic. What has to be in between here? Yeah, there has to be some sort of register in between there. Otherwise, it's not going to wait on the clock cycle. Otherwise, this is just combinational logic, and it's just going to flow through basically at the speed of light, right, as fast as it takes to go through all these different data paths and out. So there needs to be some sort of buffers in between. So we put registers in between each of these. So it shows that right here. So we put registers in between each of these. And brilliantly, right, we named them the instruction fetch decode register, right, instruction decode execute register, execute memory register, and memory and write back register. So that's where these stages come from. All right, I'll go back to the slideshow now that you've seen that picture, because now you'll better understand where this comes from. So let's go through one of the MIPS instructions, like a load word, right? How much time does it take in each of these stages, right, in picoseconds, right? So load word is basically almost 200 all the way across, except for register read and register write. So the total time is 800 picoseconds. A long time ago, what we talked about is when you're designing your CPU and your ALU, basically find your longest instruction, right? And then divide up your clock cycles, and in this case, your stages based on that. So you can see we target load word here because it looks like it takes the longest out of any of our other format type instructions, okay? As an example. So if we did, since it takes 800 picoseconds, if we did 3 load words contiguously without any pipelining, right, how long would that take?
600 picoseconds.
If it took 800 picoseconds to complete a load word, right, and we did 3 of them. Say that again?
2400.
Yeah, 2400, right? 3 times 8, right? Whereas if we pipeline them, right, and we do 3 pipelined, now you can start seeing the payoff of using pipelining in stages, okay? Now what does this assume about your CPU design? You have to have at least more than one ALU, right? Which is a very reasonable assumption with today's CPUs, right? So I mean, we're talking about millions, right? So this is reasonable when we're doing 32, 64-bit, 128-bit wide words, right? And we can shove all these through multiple ALUs and then pipeline them, right? So in the time that how do I want to explain this? So we'll start with the first one, okay? So as you can see up here, if this was doing 3 in a row, like I talked about, it takes 2400 seconds. So finally, when the register finishes, then the next instruction is fetched, finishes, and next instruction is fetched. Versus the pipeline, it goes, that's why I liked that picture of the book better than this. After instruction fetch is processed through the first stage and goes and is saved into the register and begins in what it's going to do in the read and decode, then the next instruction is fetched in that first stage. And we just keep filling up this ALU. So there's no dead time. When you do it contiguously like this, right, what happens is after this first instruction fetch goes through, the whole front end of the ALU is just sitting doing nothing, essentially. It isn't realistic. There's actually stuff going on, but nothing useful to us, right? So we maximize that time. How many of you are familiar? Is this, I mean, Greek to anyone, or is anyone somewhat familiar with pipelining? Who's seen pipelining before? Okay, so a few people. Okay, so feel free to stop me at any time. So I talked about this a second ago. Basically, when you introduce stages in a pipeline, the factor speedup is essentially, if your initial start time and finish time are not large, your factor of speedup is basically going to be equal to the number of stages. If it's not balanced, so like the first process takes a significant number of time before you can put a second thing in, right, then you're not going to get that huge factor of increase, right, in speedup. Okay. This talks about MIPS, and we're going to use, I mean, the book follows obviously MIPS the whole time, so we're going to use MIPS the rest of the time and talk about how MIPS was designed specifically for pipelining in its instruction set architecture. Okay, does anyone have any questions on that? So that's pipelining in a nutshell in stages. Yes, sir. Can you talk loud?
Just to make sure I'm understanding that, was that when we were showing the pipelining with the bars like this? That was in one ALU, right?
Right. So if you have multiple ALUs, right?
They're all doing.
Right. You can be pipelining all of them. Yeah, I should have better expressed. This assumes multiple pipelines for really good performance gains for today's CPUs, right? You can stage a single ALU, right? And you'll see the factor increase based on the number of stages, but just for that one ALU. Now, CPUs have tons of ALUs. Yes?
So if you have multiple ALUs, why do we have to wait that time for the instruction fetch? Isn't there a way you could just like fetch 4 instructions at once and then use all 4 ALUs like at the exact same time?
Right, so that's another level of parallelism that we could do, right?
Okay.
But the idea in pipelining is that, and this is why I ought not to have brought up multiple ALUs yet, because this extends out to multiple ALUs, right? The idea in pipelining is that we don't waste the time, though, now when those 4 ALUs, if you issue the instruction fetch and a load word for all 4 of them at the same time for a different memory address, right? If they're all trying to access the same memory address, you're going to have other issues, right? So presuming it's all 4 different memory addresses, right? And it goes out and fetches them, then after the fetch is completed, all 4 of those ALUs, the first stage is empty again. So the idea is fill it up, keep it busy, right? I mean, we see this all the time with fast food, right? I mean, you create stages in a pipeline essentially at McDonald's, right? I mean, you're trying to get every spot filled, regardless of where each person is in time, so there's no wasted space. So this is the same concept. Now we're not wasting any time. And realistically, it's going to be doing calculations anyways. It's going to take, if you watched what I went over in Appendix B, right? If it's combinational logic, it's just going to check whatever values are there and do something with them. Whether we use what finally comes out of the back end of the ALU or not, it's up to us, right? So since it's going to be doing something, fill it up.
Okay.
Yeah. Good question, and thanks. Does that answer your question? And does that help you understand? So we do both,
Yeah.
right? And then we get the performance gain. All right, any other questions on pipelines? Okay, all that is cool, and the words the book uses, assuming you're wearing like happy glasses and everything, there's never any issues, right? But what if, for example, what I just gave the example of a second ago, what if you have 2 instructions trying to access the same memory address, right? Or what if you have data dependencies, right? So you have a load word and then an add immediately following it that depends on the load word, the register and the load word of the instruction previous to it. Well, now pipelining is not so pretty, right? Because as the first instruction is fetched and decoded, and it decodes it as a load word, then by the time it gets to the execute, right, it's just starting to pull down that memory address, right, or in the instruction decode, right, it's pulling down the memory address now that it knows what it's supposed to do with that instruction. But the add already got loaded into the fetch, right, and is being decoded, and the add might try to pull from the register before you've even put the memory address that you were calling in the register. Now you have a problem, right? Now the add will just take whatever's in the register, regardless of the timing. It'll say whatever, I'm the next in the stage. It'll execute the add operation in the ALU and then spit out garbage, right? Garbage in, garbage out. So suddenly pipelining has some problems. So it has what's called hazards, structure hazards, data hazards, and control hazards. Data hazards are the one I just kind of gave the example of, where you have data dependencies. Structure hazards are based on the design of the your ALU itself, and control hazards are for branches, right? Branches are a whole nother problem. We'll talk about that in a second. So structure hazards are, for example, where this was what I talked about first, 2 memory addresses, same memory address by 2 instructions at the same time. It's just not physically possible with the way we've designed our memory systems. And so when it goes out to execute this in a pipeline, right, depending on your clock cycle, depending on your memory system of your computer, the first, even though it might be decoding in the first, I don't know if I'm going to be able to sit here the whole time without using the board a little bit. See what we can do. If we had 2 load words to the same memory address, as an example, right, the first load word, when it gets into the decode stage, might still have some control in memory on the memory address that the second load word is trying to access. So the second load word issues the command to your memory to touch that memory address. Your memory is going to say no, it's being read right now, right? It's still in another, it's tied up by another clock cycle. Or you might not have built logic in there that says no, and they both try to read it at the same time, and bad things happen, right? Voltages get skewed or something weird, something not considered in the design might happen. So it's a structural control issue. That's one example. We'll talk about that later. data hazards is an easier one to talk about, and this gives almost exactly the example I just talked about. An instruction depends on completion of data previous, right? So here they have add, put the result in save 0, right? And then immediately following it is subtract in S0. Okay, I'm standing up. So, for example, it's like a chain. I don't know how the video is going to turn out. We'll see. So if this is the instruction fetch, decode, this is execute, this is mem, this is write back. Okay, did I get that right? Am I missing anything? Okay. When our add is here, so this is at time 0, right? It goes in instruction, it fetches this, right? Okay, and subtract is over here. It's not even been loaded into the pipeline yet. Okay, all right. So at time 2, the instruction has been fetched. Now it knows and decoded its add, and now subtract is being fetched. Okay. In 3, at time 3, add is now, this single instruction has now made it through each of these registers and is actually executing T0 and T1 are actually being added. Okay. Previously, right, it was fetched, it was decoded, the registers were pulled and sampled into the combinational logic. Now the ALU is adding T0 and T1, right? And so subtract is now in the decode, okay? And so now the computer knows, oh, this instruction is a subtract. We knew this because we're seeing it in assembly language here. So it's subtract, right? And the ALU just finished adding. So now the result, it's trying to decide what to do with it in memory, where it goes, the add instruction, right? So we know it's going to go back to S0. It's trying to figure it out through the control, right? And now subtract is already executing. So that means back here, subtract loaded whatever was in register S0, and was S0 ready yet? Did S0 even have written back to it yet what the value was from add? No. So this is where pipelining suddenly is not so pretty. Right? We have hazards, we have issues. Does this help amplify it a little bit better? Okay, so this is a data. Data hazards are pretty easy to detect and see, and there's ways to deal with it. We'll talk about this little bubble picture that we have here in a second. But there it points to, yeah, we'll talk about that later. Well, it has it here. I'll talk about it in a sec. Let me get to control hazards. I want to introduce each of the hazards first so you're familiar with the major 3. The other one is a branch, right? So branch is also pretty easy, I think, to detect just by inspection. So if you have, I don't know, someone give me a bunch of code, a bunch of assembly instructions, and I'll put a branch equal at the end. So give me 4 instructions here. Add. So you guys were seated. What's next? Load word. Okay. Save word. Store word. All right. Okay. And then right here we have a branch equal. Okay. Well, this is similar to the first case. I shouldn't have erased all of these. Similar to the first case. Decode. Fetch. Right. Let's say the branch equals depends on this word right here that you loaded. Okay. Even though this is 2 instructions before, right? If the branch equals comparing the memory address or the register that you load from here, right? We're going to have the same issue as a data dependency hazard, right? It's just going to be one ahead this time. So load word would be here when branch equal is here, okay? And it's going to be really close. It's going to be neck and neck. So load word is here, and branch equal is already executing to determine if whatever registers it was checking that this load word occurred is checking if they're equal or not. Do I branch or not? Well, it's neck and neck. It may not have written back already because it's not completed technically until after, right? So it may not have written to the register that branch equal is comparing from. So now it branches based on some arbitrary value that was in the register. Yeah, also not a cool behavior, right? Not desirable. So that's what control hazards are, right? See if he gives a picture. Yeah, so he puts them immediately, right? In this example, I'll talk about the solutions here in a second, but he gives an immediate example, right? If you have an add and a branch equal, let's see here, does this depend on, this doesn't show it's checking either of those, but we'll talk about the solutions in a second. So those are the three hazards. Now let's talk about how to get around them. Does anyone have any questions on structure, data, or control? Okay. Again, these wouldn't happen if you just did everything one at a time, right? Because then it's almost like what you've presumed has been happening up until now, right? Kind of the way we've been presenting it is, oh, it executes this, it's done, now it does this, and it's done, now that's not actually what's going on, right? It's doing all of them almost simultaneously, or it's depending on how wide, how many stages you have. Okay, in this case we have 5, so that makes the calculations pretty easy for MIPS, okay? So how do we get around them? Let's talk about data hazards. With data hazards, what we can do is we can change the write back circuitry. I don't have it pulled up here, but that picture I showed you earlier, yeah, it's gone. We can change our data circuit, and we can say if we know that we have a situation like this where the next command instruction is dependent on the previous result, we can put some sort of flag in our design that says these are dependent, so as soon as it's executed, immediately write it back to the register. And then theoretically we'll be ready in time for the next instruction. Okay? That's a cool solution, but what do you think the cost is of that? It's more complexity, right? So that picture we showed you, we have to add another control unit, another MUPS, a write back, and another data path to take care of this situation. That's one of the costs, is complexity, right, for pipelining. Okay? So now theoretically, by writing back, we'll have it in time. So it's not writing back in time, like it's not going backwards in time, right? It's just making it immediately available, right, as soon as the execution is complete. That doesn't solve, right, if it's still decoded and it's not, you know, if that doesn't solve, there are still issues where you can have, like, you know, when it's here, depending on the way your stages are set up, this presumes that the write back gets back in time to when this next command will be in the execute phase. Okay, so you have to design your circuitry correct. So in MIPS, by 5-stage pipeline, right, with simple execution commands like this, because of instruction fetch and decode, we will have enough time. But by the time this executes, right, so these move forward in time 1. By the time this executes, right, and is read into memory, if our write back is basically in between here, right, it's going to be available just in time when subtract is executing, right? And it'll just basically blow out whatever crummy value it loaded from the register. All right, so it's called forwarding or bypassing. So we don't wait until it's stored all the way back, we just immediately write it back, and there that gets that extra data path, additional complexity. Yeah, and this is kind of what I was talking about. Can't always avoid stalls by forwarding, okay, because you can't go backward in time, and depending on what your instructions are, it may or may not get it available by bypassing to the execution in time. But it does take care of a common case like this, the add and subtract, so it's worth implementing. Another way you can avoid stalls is just rearranging your code, right? If there's data dependencies when you're writing your code, you can put an instruction or two in between that still need to be executed, can be executed out of order, and don't depend on the previous instruction. So that's another way you can do it, is just rewrite it, okay? So, reasonably, you could argue that why don't assemblers just rewrite all the code? That is significant complexity for the assembler to interpret the order, and so that is not considered a great solution at this point, okay? It's significant complexity. All right, control hazards, I introduced it. So how do we get around control hazards? Control hazards are dealt with generally a little different, 2 ways. One of them is just stalling or issuing a no-op command, all right? So a no-op command literally just puts 000 into the control path for the ALU, so it says do nothing, right? And it just stalls. We just introduce So we say we're going to introduce, let's say these are directly in between, there wasn't a store word there, right? We'll just issue a no operation command in between there, right? And it just stalls. That's all it does. So it literally just sends nothing through the pipeline. So by the time the load word is completed here, right? The no op is here, and the branch equal, and we might issue 2 in this case, right? So load word is done, no op, and then branch equal is executing, and now it's checking the registers, and load word's already done, so it's checking the correct register with the correct value. So we stall by 2 to prevent us from going down the wrong path. Okay, so there's a cost there. Okay. The other solution is branch prediction, where we take a guess. So we're at the point of branch equal or set less than or whatever you've set up your branching for, and we decide we think it's just going to take path A. So we load path A instructions into the pipeline and start executing them. Okay, what do you think the cost is of that?
Sometimes you're wrong.
Yes, sometimes you're wrong. And then it blows out all of that. And then it has to load in what actually executed. Right? Now, this isn't horribly wrong, because if we just issued no op commands, right, while we're waiting, right, then that's wasted time anyways. And then we finally know which way to correctly branch. But if we're right, now we didn't have to issue all those no op commands. Right? And we were correct. And we give the software whatever it had asked for and said, here's exactly what you asked for. It's already ready. Okay. Branch prediction is a whole separate. If you take 4200, branch prediction is interesting. It goes into a whole, it's a whole subset of CPU design. Okay. Because there's a substantial amount of gain here that can occur. I mean, where do we use branches very often in software? In if statements, right? And so where do we almost always have an if type statement or some sort of comparison statement? Everywhere. Everywhere. Okay, if that makes them valuable, a common case. In loops, right? In loops, right? We do a bunch of stuff, and then like a while is the worst case scenario, right? Because you do stuff, and then the reason we're in that loop may have changed, right? But for are pretty easy usually, because for is just some sort of continued operation until an array is finished being worked on, right? And so the branch is pretty easy, right? And there's another solution to that too called branch unrolling. That I'll put in the next video. I'm not going to put that in this. We're not going to cover it today. So this kind of is the example of what I talked about, right? If it guesses at what the next branch is, and if it's correct, then awesome. We already fetched that instruction and are beginning to process it. If we're incorrect, then all that gets blown out, and we have to load in what currently path was supposed to be taken. There's a couple ways to do this. I'm kind of getting ahead of myself today. So right there, a loop and if statements, just like you guys talked about. One of the ways that they do this is just keeping a history. I'm going to talk about this very lightly, okay, because this is a whole separate area. One of the ways to do this is just keep a history. So what small piece of memory associated with this code in the past, the majority of the time, did it take the branch or not? If yes, then we're going to guess it's going to take the branch. If the majority of the time it didn't take the branch, then we're going to guess it's not going to take it again. Okay, so we just keep a history of it, basically. Dynamic branch prediction is a whole nother area. Again, that gets a little bit outside of the scope of this class. But both of them are based on a history. So here is, now we have to add in for the hazards. So here I already talked about the pipeline registers. Here you can see the write back, and then, hold on one second, I want to get to where, okay, well this is worth just, this is what I did on the board, but for example, a load word going through the pipeline, right? So here's the load word instruction fetch, instruction decode, execution, and then memory. So those are the stages, and then write back, okay? Yeah, but we have to correct this. So this was the additional logic I said we have to add for write back and path forwarding, and it should show it right. It doesn't show it yet. Here's another way to illustrate the stages. That's a little easier to picture than drawing out the whole ALU path, right? So this is just kind of a simplified drawing, and this is kind of what I was doing on the board. Does everyone kind of track how this flows, this graph? So you have your instructions on the left, and then there's stages on the right, and you can kind of see in what clock cycle, 1 through 9, when they're going to finish. This is just for representation, so you can view it. Can you guys see it in the back? Yeah? All right. Here's with the actual information written out. These are all just different ways of seeing it, okay, going through the pipeline. This is what closer to what I was drawing on the board, showing where everything is at, in an instance of time. Right? So here this shows where add is at one instance of time, where this load word is, where this add is. It shows where each of them is at an instance of time. And these things are happening, you know, in fractions of a second. So this is, we're assuming we can see it. So here is what we have to add. Here's the penalty that I was talking about right here. Which one do I want to do first? Let's do this one first. Here's, I fixed this, and it's still showing on top of it. All right, here's the penalty we have to pay. So remember, we added these registers in between each stage, so that saves the state, right? So we have IFID, fetch, decode, decode, execute, execute, mem, and write back, right? Now we have to add to those registers what control logic we needed to do because of data dependency and data hazards overall, like a data dependency or a data control hazard, right? So we have to add additional control. So here's the decode logic and where in memory it's going to have the information. Okay, so that's the price we pay. So you'll see in a second here, there it is. So now remember, before we had all what was in black for the ALU, because we want to be cool in pipeline and we want to use every fraction of a second, we have to add all of what's in blue. Additional logic. Yeah. So
Extra wiring.
yeah, it is, right? So it all starts right here, right, in the second stage, right? You see that? Because that's where, right before we get into the execute, we need to start. We need to mark and indicate in advance before we do the execute what to do with it after the execute. Right? We need to flag it, right? Does it need to be written back? Is this a memory value, or is this something the next execute might depend on? And then once we've flagged those, we need to add the additional logic to send them back to where they all belong in time. So it's probably adding, I mean, just by visual inspection, it's adding at least a third additional circuitry for pipelining. Does anyone have any questions on that? Okay. Is everyone able to follow so far the difference now, where traditionally I've just shown you, we presented, oh, it's a single instructions executing at a single time versus how we're filling the stages every cycle. Does everyone follow that explanation? Okay. So this is all good, but what we haven't talked about is we presume that it just knows, we haven't talked about how it knows to detect these, right? How does it detect these, like a data hazard, right? We just added the circuitry and said it knows. We didn't talk about how, right? So there's ways that we can detect that, right? So this is a good example. I mean, this has a ton of data hazards in it, right? The and depends on the subtract previous to it. The or depends on the and, or the subtract previous to it. Add depends on the subtract. And then store word, I mean, they're all dependent, and they get changed along the way. So you've got multiple issues. So how does it detect these? In between the registers, it does operations to determine, I'm not going to go too far in this, what register, if one register, those additional registers we added, depend on a previous register. Once we had logic that can check those, right, then it can see if they're equal anywhere along the way. And if they're equal anywhere along the way, then it sets the flags for we need to go back. This needs to get written back immediately. okay, or bypassed or forwarded, okay, for a data hazard, for example. All right, so it detects the need and sends it back. How are we doing on time?
It's 5:26.
So, all right. Here it just focuses on the forwarding path. So this is just zooming in so you understand specifically where the forwarding path goes. So after the execute, it goes, now we've added this logic right here. It goes both to the data memory, it goes, and then it goes all the way back to where it's going to be forwarded, right? And all the way back to the forwarding unit from these additional registers that we added. So today overall, based on what I showed you like a month and a half ago, we're basically doubling our ALU size because we've added both all these registers, the control, which this is zoomed in, it doesn't show all of it, in between them, and the kind of micro decoders in between all of those two. All right? Yes, sir.
Are those just reserved for the like the ALU and the CPU, or are those like part of the 32 registers that are including the MIPS instructions? Like the ones that we added right here.
Right. So you're asking if they're part of the registers that we can access in assembly? No, these are in the stages, right? These are state logic or sequential logic, right? In the stages. That's a great question, Jordan. I don't think there's a way I can access those. I personally wouldn't want to because I wouldn't want to mess them up. But I don't think so. I don't know though, for certain. This goes into more depths. You can look at this in the book. I don't have enough time to go over all of it, but specifically it's just setting up the case statements of how we can detect when there's data dependencies. And these fancy words are just references to those stage registers, right? This is the execute memory register on the right side, and it's comparing it, right? It's doing an AND to compare it and get the result. Okay, that's the additional logic. Okay, so I already talked about this. This is just showing the control of it. And this is showing another image of it. So today, like, it's a lot of pictures, okay? But a lot of it is synonymous. We're repeating the same thing. We showed you on the Datapath circuit layout. Now I'm showing you on a graph of clock cycles in staging what it looks like, right? So in this case, the load word, whatever is getting loaded into, we'll say this is save 2. I mean, they just drop whether it's save temp or whatever. It's getting loaded into, we'll call it save 2. It's just showing you that by clock cycle 4, it's completed and it's getting written back, right, in time to go through that clock cycle, right? But in this case, you can see obviously this isn't in time enough. So even still, sometimes you'll have to stall. Right, because we can't go backwards in time. It's just going to go straight down. Right? This is not realistic. This is realistic. I kind of talked about this already, how to stall the pipeline. Right? We just throw no ops in there, or we can reorder our code to do other stuff. And the text shows it as little bubbles, stall bubble. So right here you can see it just. Does the last slide? It doesn't. So this presumes that our initial set of commands was load word and or add. Okay. It detected the hazard, right, and inserted. It drops the and down, inserts no op here, right, and it just executes the and one clock cycle later. Okay. So you want to have any questions on that? So this is just, I talked about this is just laying it out another way. Okay. This is showing where the hazard detection unit is. This is the logic I told you we presumed previously just knew on its own. This is where the logic actually is retained. What's that? Did someone have a comment?
He's been doing like a hip quiz.
Oh, all right. Okay. So that's about what I want to go over for today. We can touch on these. Let's touch on the predictor real quick. So there's just a sample of branch predictors. A 1-bit predictor basically just tells if the branch true it was taken or false it's not, and is stored in memory. The problem with a 1-bit predictor, right, is it can be wrong up to 2 times before it's updated, right? So if you just use a 0 or 1 in memory, it could be wrong twice. So before you update it with the history, so you may not actually be doing yourself a favor. It may be wrong more often than it's right, okay? In big picture. So the solution to that, right, 2-bit predictor, nothing really genius here. And then they show the finite state representation of this, which I talked about in Appendix B presentations. So basically, it's either in a 1-1 state, prediction was taken, a 0-1 state, the predict was taken but not last time, and or in a 1-1, 1-0, or 0-1, predict was not taken last time, and then finally 0-0, which is it wasn't taken the last 2 times. So you have a smooth transition. So theoretically, you only transition once when you're wrong once, and not 2 times. So this will be statistically more often correct, theoretically, like just pure permutation math, right, than a 1-bit predictor. So that's why I said I won't go a lot into this today. This is like a whole nother, this is 4200 goes into this a whole ton. You could even write a program on it, I think, at 4200. So it's a whole nother area. Something else that can be done is you can fill a delay slot. So if you know, going back to, okay, this example, right? We had a store word here, okay? So if you, you do the add, it's going through there, you do the subtract, it's going through, going to load word, going to store word, so 1, 2, 3, 4, 5. So 5th stage, by the time we get to branch equal, this add is in the 5th stage finally, okay, and almost completed, okay? So let's say our branch equal depends on that. Well, something you can do is you can look at the branch history, right? You can also add a delay. If you know the branch is commonly taken, okay, and it depends on this, right, then you still can't compute it in advance yet because you're waiting for this, right? So you just insert another command from down here that doesn't have any dependence on these, okay? That its order doesn't matter. So instead of a no-op, instead of, because in this case, this was already loaded, but this is dependent on here, we can't go any further, so we just delay by putting other commands that can be accomplished in front of this. Like it shows just rearranging it. Just rearranging it. You can put whatever, I don't know what's down here, but another add I, let's say, right? So we just move that up here, and it may have nothing to do with this or the path that's taken. Or this may be the next step after this. You have to really kind of think about this. After this is completed, this may be the next step on the branch down here. And it loaded it up and started it a little bit because it has no dependency on this or that. So this is where the dependencies get interesting because of pipelining. Okay, any questions on any of that? Okay, I think that's about, yes, that's about it for today. I'm going to post another video talking about exceptions, further detail on handling, and there was one other thing, oh, and loop unrolling. That will be in the next video. Okay? Does anyone have any questions on that? That puts us just under an hour. Okay, let's take a 10-minute break, and then we'll take the quiz.